Well, good evening or good afternoon, everybody. This is Mr. Kinney. This is the Molarity test review. This is part 2 that I'm going to go over. So this will be the second half of the review sheet. These are the questions that my period 6 and period 4 class wanted me to go over. So let me see here. So to begin with, let me start up over here. I'm assuming if you're working on this, you've got the questions in front of you, so I'm not going to worry too much about trying to keep everything perfectly in view up there. So one of the parts per million, I'm going to start with number 27. Parts per million is going to be equal to the milligrams of solute divided by the liters of solvent, the total solvent you have. So in this problem, we go to set this up. I'm going to go ahead and get this set up first with grams. We have 7 grams. And I'm going to go ahead and convert grams into milligrams. So just like there's 1,000 milliliters in a liter, 1 gram is 1,000 milligrams. So that cancels. So basically, we've got 7,000 milligrams of solute in this problem. And it says it's dissolved in 800 milliliters of solution. A lot of you know that just when you divide it by 1,000, you scoot the decimal place over 3 to get 0.8 liters. If you're not sure about how to do that, you have 800 milliliters. 1,000 milliliters is 1 liter. So the 1,000, basically you just move this decimal place over 3 and it becomes 0.8. So we got 0.8 liters. So when you go to do the magic work on there, well, I'll let you do that. You've got 7,000 divided by 0.8. You can do something over there. Go and hit pause and punch that out. And then your answer, when you punch that out, your answer is going to be milligrams per liter, which is what parts per million is. Question number 28. You've got a concentration of salt water is 35,000 parts per million, and you have a 2-liter sample. How many grams are dissolved in it? So let's always start with the base equation. Parts per parts per million is milligrams per liter. And in this problem, we know that we have, let me use a different color. Our parts per million is 35,000 parts per million. We have 2 liters over here. So what we have to do is we can solve for what milligrams are. But then when we get to milligrams, we have to convert it to grams. So let me see. You know what? I just love to rearrange equations. I want to get milligrams all by itself. So I need to multiply. Let me get rid of these for the moment. I'm going to multiply both sides by liters. That gets liters. Gets the L out of the bottom here. And we got milligrams will be equal to liters times parts per million. We have 2 liters. Pardon me. Times 35,000. Now, this is milligrams per liter. It's parts per thousand, but that's what milligrams per liter is. This lets us cancel out the liters. Now, we're going to end up with 70,000 milligrams per, just milligrams, but we want grams. So now we got to convert it into grams, and you should know that 1,000 milligrams are going to be 1 gram. So now the milligrams cancel out. These 3 zeros will cancel out those 3, and there you go. 70 grams will be your answer. Now we've got the solubility chart to look at. And please just remember that solubility and usually these charts, they're going to tell you these numbers that we figure out are going to be how many grams of solute, usually a salt, that can dissolve in 100 grams. There's a little cup I like to draw, a beaker that's got 100 grams of water in it. And these charts tell you how many grams of solute you could put in here until it gets it saturated, meaning it can't hold anymore. So, this question, how many grams of potassium nitrate, here's potassium nitrate, can be dissolved in 300 grams of water at 50 degrees? Well, the chart, okay, so at first you might go, oh, I don't know how to do that. Well, let's first figure out how much can be dissolved in 100 grams, which is what this chart shows. So we want 50 degrees, so we're going to come over here to 50 degrees. We're going to go to potassium nitrate, and we're going to go up the chart to potassium nitrate until the line 50 degrees. We hit potassium nitrate. Looks to me like it's pretty much right in the center. Come over here, and it looks to me like it's 85 grams. Now, this isn't the answer yet. We're working on 85 grams of KNO3 can be dissolved in 100 grams. I'm going to put in 100 grams of water. That's what this chart tells us. Let me double check. 50 grams. Excuse me, 50 degrees. Come up to here. We hit potassium nitrate. I'm on the right one. Okay, so about 85. But now we're setting a proportion, because now we're going to be answering the problem. How many grams? X grams can be dissolved in 300 grams of water. Well, let's see. We need to find out what the solubility is here. Now, I can tell you right now, we've gone from here. We've gone from 100. This is the solubility in 100 grams. Here's 3 times the amount. 100 times 3 is 300. So the answer is going to be 85 times X. Excuse me, 85 times 3. Now, if you can't do that in your head, if it's not an easy one on the test, let's just go ahead. Let's just solve for X. Let me get another color here. Let's multiply both sides by 300 grams H2O times 300 grams H2O. So now the 300 grams H2O cancels out over here. Over here, 100 grams H2O will cancel at least the 2 zeros on the grams H2O, and we get 300 divided by 100, or 3 divided by 1. So basically it's 3 times 85 equals X. You can do the math. I won't do that here. Question number 31. Which compound shows the greatest increase in solubility? Okay, hold on a moment. When we take a look at these solubility graphs, this is showing that as we get hotter, the solubility is increasing. It's more. Most compounds, when they dissolve in water, they will, when you heat them up, they're going to become more and more soluble. Now, there are some exceptions. We see these dotted lines here. Here's hydrochloric acid. Here is ammonia. And here's SO2. These tend to very often, they can, when they get warm, they tend to turn into gases. And gases have as they get hotter, they can't hold as much. You know that with a soda. You open a warm can of soda, it's going to fizz and bubble a whole bunch of gas out because the gases can't be contained. They're not soluble in warm water. Anyway, let's come back here now. So we've had our increasing solubility, decreasing solubility as we increase the temperature. Which compound shows the greatest increase? Greatest increase. Okay, so now we're looking for the steepest line from 0 to 100. So we're going to go 0 to 100. We want to see has the greatest increase. Well, basically it's the slope of the line. And I'm telling you, it looks like potassium nitrate has the steepest line right there. I don't think anything's got a steeper slope than that. So it's going to be potassium nitrate. Okay, so that's the one that's got that one you can dissolve more and more and more as you heat it up. At 40 degrees, over here on the chart, 80 grams of sodium nitrate are dissolved in 100 grams of water. Okay, is this solution saturated, unsaturated, or supersaturated? Well, let's take a look here. First off, I want to see, I'm going to look on this chart to see what the solubility is for sodium nitrate at 80 degrees. Here's 80 degrees. And where's our friend sodium nitrate? Where are you? Ah, there we go. Here's sodium nitrate right here. Here's 80 degrees. And oh, whoa, look at that. It looks like it's just above the halfway mark, which I'm going to call 146. 146 grams of sodium, if I was calling that potassium nitrate, sorry, sodium nitrate will dissolve in 100 grams of H2O. That's what this chart tells us at 80 degrees. So now we know the solubility at 80 degrees. Now let's look at our data. They're saying at 40 degrees, uh-oh, did I look at the wrong one? Doggone it. Oh, I'm so sorry, I got you messed up there. I was getting these mixed up. So, sorry, got to back off. We got to look at 40 degrees. So, sorry about that. 40 degrees. Okay, sodium nitrate. Sorry about that. That looks to me like when I go to 40 degrees on the chart, and then we come over, that looks like that's going to be about 103. It looks like it's a little bit below the halfway. So 103 grams of sodium nitrate will be soluble in 100 grams at 40 degrees. It's always good to double check those answers. So now we're going good. Now let's answer the question. If you had 80 grams dissolved in here, well, at 40 degrees, we can have 103 grams of sodium nitrate in 100 grams of water. If we only have 80, okay, so if we have a solution that's 80 grams in 100 grams, we can hold a whole bunch more. We could probably add just about, let's see, we could add 23 more grams to this solution to get it to where it's at the point of solubility. So the point here is this solution right here can hold more solute, so it's going to be unsaturated. When you look at these numbers off the data table, this right here, this is telling you what the concentration is when it's saturated. A saturated solution would be 103 grams in 100 grams. But the one they gave us, 80 grams, oh, that should be grams right there. There we go. This is unsaturated. We could add a whole bunch more. Sorry for the blooper. Last time, I'll apologize. A saturated solution of ammonium chloride. Okay, we look at our chart. Where's ammonium chloride? There we go. It's this line right there. Our chart. So a saturated solution is formed from 100 grams of water. Okay. If the saturated solution is cooled from 70 to 50, how many grams will precipitate will form? Okay, so first, let's find ammonium chloride at 70 degrees, pretty warm. And, oh, where's the ammonium chloride? I keep getting that mixed up. Ammonium chloride, which one is it? It's this one right there. And we're at 70 degrees. I don't want to mess up. It looks like when we go up, it's, oh, I think it's just barely above 60. It looks like, I'm going to call it 61 grams of ammonium chloride can be dissolved in 100 grams of H2O at 70 degrees. Now if we cool it, okay, now we're going to go from 70 degrees to 50. We're going to come up here to ammonium chloride. It looks like it's 50 grams of ammonium chloride can be dissolved in 100 grams of water. And this is at 50 degrees. So what happens, it can hold a lot more when it's hot. It's going to lose some, when it cools down, it's got to dump. Let's see, the difference between these two is 11. 11, as it cools, 11 grams of precipitate, of solid, will form. I'm going to abbreviate that PPT. Because when it's warm, you can hold this much. When it cools down, it can only hold 50 grams in this much. And so we have to drop off. You have to get 11 grams of a precipitate formed in the bottom. Number 34. Describe the solution dissolving process of an ionic compound. Well, it's not a really good video where you've got the different ions in, say, a salt crystal like this. And what happens is you've got water molecules that come. Now, water molecules, this side of the water molecule is slightly, this is the oxygen side, slightly negative, electronegative. The hydrogens over here are slightly positive. So what tends to happen is the negative ends of the oxygens tend to gather around a positive ion, and then they pull it off and separate it in solution. And then you get on the negative, oh, I didn't mean to make a division sign. Then you get the on the positives, you're going to have, excuse me, on the negatives, you're going to have the positive end of the oxygens. So what happens is the water molecules, basically, they surround this so that a negative ion is going to have the little plus parts of the oxygen kind of stuck to it. And a positive ion is going to have the negative parts, the oxygen end, attached to it. That was from a video. If you want to see that process, there's a really good diagram of that in the World of Chemistry available on my website. You can get the link. Okay, now a lot of this stuff, how does stirring, okay, if you stir solution, you're just constantly bringing fresher water, and fresher water allows for faster dissolving. Increased surface area. If you have a big chunk of salt, like we did in the lab, salt rocks, and small ones, these guys, the small ones, are going to dissolve much quicker because even though they're smaller, their surface to volume ratio, they have much more surface to volume ratio. Their surface is really huge. Where this one over here, the surface to the volume is so much bigger, the surface to volume ratio is smaller. I'm going to draw it physically smaller. Even though this is huge, if you dissolve away this thing, by the time this one's dissolved away, you've probably only barely etched the outer part of this. You might not even notice that this thing has started to dissolve at all. It takes much longer. And increasing the temperature. If you increase temperature, you just make that you've got the water molecules are just moving faster, and they're going to hit dissolved solids quicker and more often. And so the more times, it's almost like you're doing like the increased temperature. It's kind of like stirring the water, bringing fresher water to it. Okay, on the back side, last 4 questions I'm going to go over. What will happen when one salt crystal is placed in a solution that is unsaturated, saturated, and supersaturated? Well, if you have a solution that is unsaturated, that means it's slightly salty. You drop a salt crystal in here, it will dissolve away. It'll dissolve. If you have a saturated solution, that means it cannot dissolve any more salt. And if you drop a crystal into it, the crystal will just drop to the bottom and sit there. If you have a solution, and these are fairly rare, but if they're supersaturated, you're either going to see crystals already sitting on the bottom, or it could be one of those weird ones where if you cool it slowly and don't agitate it, it doesn't do anything until you add the crystal. And then it goes crazy. It starts adding a whole bunch. All of a sudden, it's almost like magic. A lot of times magicians might do that with kind of where they get a supersaturated solution, put just a little grain of something, and it looks like you're getting a bunch of stuff from nothing. If the solute is a polar molecule, should the solvent be polar or nonpolar? We're assuming if we want them to mix. So if you have a polar water, a molecule like water, and you want it to mix, you need to mix it into a polar molecule, either like water. In the lab we did alcohol. They can mix together. If the solute is nonpolar, like oil, should the solvent be polar or nonpolar? Well, this is nonpolar. If you want stuff to mix, to be miscible, they need to be of similar polarity. So nonpolar solutions will mix into nonpolar. Polar solutions will mix into polar. If you mix water and oil, well, you know you're going to get a layer of oil on the top because it tends to be less dense, and then you're going to have water down here. And lastly, the word miscible just means that it can mix. It's mixable. I wonder if that's a derivation of where we got it from something. Anyway, there you go. So I'm done. Signing off from room 901.